Hello everybody, this is Dr. Christopher White and welcome back to part 3 of Deformation. Alright, so we finished part 2 with this picture. I think we can probably all see what's going on here. So remember, in this picture we have two structures. One is an anticline, one is a syncline. So remember, an anticline is going to form an arch and a syncline is going to form a trough. Okay, so I think we can probably pick out the features. So there we have an anticline. Now remember, anticline, oldest rocks in the middle, youngest rocks on the outside. So these rocks down here in the core of the anticline, they're going to be the oldest, and these rocks on the edge here, they're going to be the youngest. Then we have the syncline up here. Should have said, there's the axial plane, because once again, this is a nice symmetrical looking anticline right there, isn't it? So there's our axial plane. And up here we have a syncline, you can see the trough shape there. So that means in the case of a syncline, the youngest rocks are going to be here, and as we move progressively this way, the rocks are going to get steadily older. And once again, pretty nice symmetrical syncline, so we have ourselves a nice vertical axial plane there as well. So that's a pretty beautiful example of what's referred to as an anticline-syncline pair. And one of the things about anticlines and synclines is they do occur together. Okay. Typically, if you spot an anticline, there'll be a syncline somewhere nearby. Okay, so now let's think about the geometry of our folds. So as we've discussed, a fold has this kind of shape, and now a fold has two limbs, one limb and the other limb. So a limb is either side of the fold, and the hinge is the point where the two limbs meet. So these are the basic parts of our fold. You have two limbs and a hinge. Now, think about this. Most folds, if they were perfectly horizontal, they would go on pretty much forever. However, if we go all the way back to that picture of the Appalachians, what do you remember? We saw the valleys coming together and joining up to form a point. And that's because most folds are not nice and horizontal. Most folds plunge, they dip into the earth. And so that produces what we refer to as a plunging fold. And you can see it here. So look at this diagram here. In this case, you can see if we were to come along this side and come along the other side, eventually both sides of the fold join together and they form a point. And that's just what we see in that diagram of the Appalachians, isn't it? So the fact that the fold is plunging down into the earth means that eventually both sides of the fold will meet up and they'll finish in a point, just like we saw in that diagram of the Appalachian region. So we've already gone and described the axial plane. Now in this case it's been called the axial surface. Axial surface and axial planes are kind of interchangeable terms. I've got to be honest, axial surface is kind of the more up-to-date term, but having been taught by rather old-school geologists, I personally prefer the term axial plane. Now in this case, as we've also discussed, the folds are upright, so that means the axial plane will be upright. But of course, as we start to push our fold over, in this case we have an asymmetrical fold, you can see the limbs are different lengths and different angles. We can see as the fold begins to go sideways, so does the axial plane. The axial plane will begin to tilt with the fold. So in the case of an overturned fold, or an overfold is also called, remember one of the limbs will be vertical. Okay, so if you look at this asymmetrical fold, this limb here, it's close to vertical but not quite. This fold here, this limb here is vertical. So this is going to be a symmetrical fold, this is going to be an asymmetrical fold, and this is going to be what's called an overfold here, or an overturned fold, also referred to simply as an overfold. And you'll notice that once again, as the fold begins to lean over, the axial plane will go with the fold and it will get more and more steep. In terms of the fold axis though, if you just ignore the axial plane, just think of the fold axis, it's a straight line that runs like that, it's a straight line that runs like that, and it's a straight line that runs like that. So the fold axis tells you nothing about whether the fold is upright or leaning over. All it tells you about is which way the fold is orientated. So the axial plane here is running this way, so I know the orientation of my fold same here, and same here. So once again, just going back to our plunging folds. So this is our situation. So here's a situation where you can see we have a plunging anticline going this way, a plunging anticline going this way, and a plunging syncline going this way. Okay, so these are our folds. You can see there's our anticline, there's our anticline, and here's our syncline. Okay, now over time erosion is obviously going to kick in, and remember, some of these layers of rock are going to be more resistant to erosion than others, so some of them will form high ground, some of them will form low ground. And so for argument's sake, what we're going to say is we're going to say that this, by the looks of it, this, let's try and get this right, these sandstone layers here, the yellow layers, they are more resistant to erosion than this grey layer and this brown layer. And so the grey and brown layer, they're going to erode away faster. And so over time, what you're going to end up with is a feature that looks like this, where the sandstone layers are forming the ridges, and the grey layer and the brown layer have been preferentially eroded away because they're slightly weaker. And because the folds are plunging, it results in this triangular shape. Essentially, it results in the folds closing up and terminating in a point. And this very crude diagram drawn by me over here, and yes, it is tremendously crude. So this is a normal fold. Now remember, if the fold wasn't plunging, it would, in theory, could continue forever. Now, because the fold is plunging, this green dotted line, that represents the surface of the Earth. And obviously the white fold here, that's our fold. And what happens is once the fold gets eroded away, once all this excess material above the modern surface of the Earth has been lost, the trace of the fold on the surface is going to look like that red line there. Okay, and that's exactly what we see here. We get this, essentially both sides of the fold coming together and terminating at a point. And so this is a clear indicator of a plunging fold. And so here we have a really nice example of a plunging fold. This is a pretty spectacular photograph, I think you all agree. And we can see straight away, so here's one side of the fold coming this way. Here's the other side of the fold coming this way, and obviously our fold is meeting up right here. And so we know the fold itself is plunging towards us. So if we just go back to the previous picture, we can see the plunge of the fold is moving towards the point here. Okay, so in this case we can see the plunge is coming towards us. We can see the rocks diving down into the earth in front of us, can't we? So the anticline is coming straight towards us here. Now, how do I know it's an anticline? Well, I know it's an anticline because I can actually see the angle of the rocks. If you look carefully, you can see these rocks are angled like that, and these rocks over here are angled like this. So the rocks are coming up and back down the other side again. So it's an anticline, coming up and over, up and over. Okay, so this is quite a nice anticline. But you can see this anticline is plunging, it's plunging straight towards us, and we can see both sides of the fold closing up, essentially forming this point right here. So there's our fold axis, very badly drawn on. Actually, I should have redone that again. Not my best work, I've got to be honest. And of course, that's going to be our direction of compression, isn't it? If we know our fold is orientated like so, well then we instantly know which way the rock had to be compressed to produce that fold. So we know the rock has to be compressed from this way and this way. Okay? Because remember, compression has to be 90 degrees to the fold. So if this is the fold axis, it must have been compressed 90 degrees to that fold axis. So the final feature that can be formed is a monocline. So a monocline is sometimes referred to as a half fold. So here we go. So this is an example of a monocline. So in a monocline, we have horizontal rock here, then it drops down, and then it goes horizontal again. So essentially, it's kind of a kink in the layering. So flat on one side, bends, flat again. Okay. Now, most monoclines are actually resulted to faulting, and we'll see that later on. So typically there's a fault somewhere down here which is making the rock do the bending. So a monocline is, as I say, sometimes called a half fold, and it's the final type of ductile deformation. So we have anticline, syncline, monocline. In this picture here you can see not the best picture of monocline, but not a terrible one either. You can see as you come along we have horizontal rocks here, then the rocks begin to bend down, and then as we come out the other side you can just see the rocks becoming horizontal again right there. So the rocks are coming along, going down, becoming horizontal again. You can just see the transition there. Now in terms of folds themselves, so once again we discussed recumbent folds. Now a recumbent fold is the most extreme type of fold. So in the case of a symmetrical fold, asymmetrical fold, an overfold, the fold is still upright. In the case of a recumbent fold, it's been pushed so far the fold has literally fallen sideways. So if we have a look at this picture here, can anybody spot the recumbent fold? I'm sure some of you got in it, but yep, it's right here. You can just see it right there. There's the recumbent fold. So there it is marked out there in white. And so if we think about where the axial plane of this fold is, it's right there. So as you can see, the axial plane in this fold is now horizontal. Okay, so that's a nice example of a recumbent fold. Now that's typically produced in areas which have undergone very extreme deformation. So the deformation was so extreme that folds actually got pushed over. And I think, if you really put your mind to it, that's quite difficult to do. Now, if we look at this picture here, what we're going to see is we're going to see a beautiful example of an overturned fold. So what's going on? Well, what we can see is we have one limb of the fold coming in here. Then we have the fold coming round. And then you'll notice the limb of this fold is vertical. So these rocks here, they are vertical. This is therefore an overturned fold, or also referred to as an overfold. Then as we come out the other side, lost the pointer, there it is. As we come out the other side, the rocks go back to normal. Okay, so everything looking good. Vertical, normal service resumed. Okay, so in this case, track that layer, there it is, follow the red line, that's showing you essentially the path of the folded rock. So there are the axial planes for our two folds. So here we have essentially an anticline, here we have a syncline. Remember, anticlines and synclines tend to occur as pairs. So obviously, if we're thinking about it from which layers of rock are the oldest, which layers of rock are the youngest, well obviously, core of the anticline here, that's got to be the oldest. Coming to the edge of the anticline here, that's got to be the youngest. So follow this layer of rock here. Comes around, comes around, comes around, and then that one becomes the core of the syncline, doesn't it? So this is the youngest layer of rock here, and these are going to be the oldest rocks here on the outside of the syncline. So you can see quite nicely how the youngest layer of rock becomes incorporated into the core of the syncline. Now in terms of what's going on down here, you can see actually right in the middle of this anticline-syncline pair we also have a whole lot of deformation in here. Okay, so you can see that right there marked out in red. Okay, so a very strongly deformed area right here. Now you can see you've got all these little folds in here, but now the most important thing is let's trace the axial planes of these folds. Well, there they are. Okay, so if I do that, if I train the axial planes of these folds, you can see everything lines up, doesn't it? So these axial planes match up very nicely with these axial planes here. Now this is something that geologists look out for, and because all these axial planes match up, that means in all likelihood all these folds were produced by the same event, as the same deformation event. Now if however I had some folds in here where the axial planes were at completely different angles to these folds here, well that would tell me that something is going on, and those folds had probably been produced another time, either before or after this event. Okay, so geologists will always be keeping an eye out for that kind of thing. So here's another nice example of an overturned fold. Now this one's actually quite an extreme one. This is kind of the middle ground between an overturned fold and a recumbent fold. So you can see here's our fold here, and here's a Another fold here. You can see once again we have the anticline, syncline pair. So here's the anticline, there's the syncline, and you can see this is the overturned limb. It's actually gone beyond vertical. It's nearly at the point where this fold here and this fold here, they're nearly horizontal, aren't they? They're so very close, they're not quite there. So this isn't quite a recumbent fold, but it's pretty close. So this is what happens when you kind of are on the transition from a overturned or overturned fold into a recumbent fold. Okay, now the final couple of features we're going to talk about when it comes to folding are domes and basins. Now, domes and basins are a slightly different thing. So a dome is essentially a dome-like feature where you have layers of rock which have been uplifted, and it produces a circular or elliptical feature. Now, just like an anticline, the oldest rocks will be at the center and the youngest rocks will be on the outside. So a dome is somewhat akin to an anticline, but whereas an anticline will form a linear feature, a dome essentially is a circular or elliptical feature. Then we have a basin. A basin is a bit like a syncline. You'll have the youngest rocks in the middle and the oldest rocks on the outside. But once again, just like a basin, just like a dome, it will form a circular to elliptical shaped feature on the surface of the Earth, rather than a syncline which will form a linear feature. Once again, think about the image we saw right back at the beginning of the Appalachian Mountains. All those folds that we saw were long and linear, weren't they? Whereas this dome here and this basin, these are circular to elliptical shapes. So these two stylized diagrams just kind of show you what's going on. So here we have ourselves a dome. Remember, if it's a dome, oldest rocks in the middle, youngest rocks on the outside. If it's a basin, youngest rocks in the middle, oldest rocks on the outside. Okay, so let's think about domes. So here's an example of a dome, okay? And so what can we see going on here? Well, the vast majority of domes are caused by intrusion. So under the crust here, there's an intrusion. And now remember, once again, an intrusion is magma, and magma is naturally buoyant. It wants to rise. And so our big ball of magma is rising through the crust, and eventually it gets stuck just below the surface. It can't quite make it to the surface, so what does it do? Well, it pushes up the crust above it, and it makes it dome upwards. Okay, so what we're seeing here when we see this dome is we're seeing the result of the crust being pushed upwards. And if you look down here, you can see right this area in this kind of blue-grey, that actually represents the granite itself that was doing the pushing up, and then we have the rocks that were domed upwards on the outside here. If you look at the cross section, we have the granite in the middle, which domed up the schist and the limestone and the whole load of other rocks over here. So the entire sequence has been pushed upwards because of this granite wanting to rise further in the crust, but getting stuck just below the surface. Okay, so that's a dome. So domes are relatively simple. Now, in terms of basins, basins are a little bit more complicated. So basins are the result of what's called down warping. So if you think of it, so the mechanism is actually quite straightforward. If you have a situation where you start depositing huge amounts of sediment onto the surface of the Earth, well, what are those huge amounts of sediment going to do? Well, they weigh a lot, don't they? They will literally start to push down the Earth's crust. And as they start to push down the Earth's crust, well, they start making a natural depression, don't they? Well, what's going to happen to that natural depression? It's going to fill with more sediment, which is going to push the crust down even further, continuing to cause that natural depression, which fills with even more. And as you can see, it's a self-defeating cycle, really, isn't it? The more sediment that gets dumped, the more it pushes down the crust, creating that depression that just fills with more sediment. And so the weight of all this sediment pushes down the crust, makes it bend downwards, makes it flex downwards, and that's referred to as down warping. Now, you can also get basins caused by tectonic processes, but the vast majority of basins are the result of down warping due to huge amounts of sediment being deposited in an area. So the classic example of a basin here is the Michigan Basin, and you can see it quite nicely. This is a really beautiful basin. And you can see, if you actually look at a geological map of Michigan, it actually looks like a bullseye, doesn't it? And what do we have? Well, you can see in the middle here, we have Upper Pennsylvanian beds. Then we have Lower Pennsylvanian, Upper Mississippian, Lower Mississippian, Devonian, Silurian. So we're getting older as we go outwards. Remember, youngest in the middle, oldest on the outside. So we're getting older as we move outwards. That's going to be the sign of a basin. Because remember, basins have the youngest rocks in the middle, the oldest rocks on the outside. And as you can see, it's definitely a circular feature because, well, you can't really miss the fact it's circular. So it's got to be a basin. Okay, so next of all we need to think about how we're going to describe the orientation of geologic structures. All right, so here we have a piece of rock. Now, one of the things that geologists have to do is we have to be able to take information like this. So when we walk up to a piece of rock, we have to take the kind of information we need to understand what's going on. So when you think about it, what are the 3 pieces of information that we can get from this piece of rock? Well, the first thing is what's referred to as the dip. And the dip essentially is the angle relative to an imaginary horizontal plane. So if I believe there's an imaginary horizontal plane here, the surface of this rock here, so what's the difference between this imaginary horizontal plane and the surface of this rock here? It's 30 degrees. So this layer of rock here has an angle of 30 degrees. Now, because all of these pieces of rock here are attached to each other, I know this piece of rock here will also have a dip of 30 degrees. You can see there it is. It's dipping down into the ground at the same angle as this surface here, isn't it? So the dip of this rock is 30 degrees. So that's the first piece of evidence that I can get. The next piece of evidence I can get is, what's the direction in which the rock is dipping? So I can see this piece of rock is dipping this way, isn't it? It's not dipping this way, not dipping that way, and it's not dipping this way. So for argument's sake, let's say this is north, this is south, this is west, and this is east. So in this case, this piece of rock would be dipping 30 degrees to the east. Because you can see the rock is dipping down this way, and over here is east. Okay. Now, typically when geologists refer to the dip direction, it's called, we don't use north, south, east, west, we use numbers. So north would be 0, 0, 0. East would be 0, 9, 0. South would be 1, 8, 0. West would be 2, 7, 0. And so that's how we essentially write them down. So we use a 360 degree circle. So, okay, so far we have 2 pieces of evidence. We have the dip, which is the angle at which a piece of rock goes down into the earth. Remember, the dip is taken essentially against a imagined horizontal plane. And we have the dip direction, which is the direction in which the piece of rock is dipping into the earth. Now, the final piece of information we can get is referred to as the line of strike. The line of strike is 90 degrees to the dip direction. Okay? So, we have 3 pieces of information. We have the dip, so that's the angle. We have the dip direction, which way the piece of rock is dipping into the earth. And we have the line of strike, that is 90 degrees to the dip direction. Okay, now you'll notice right here there's a little symbol, okay, and it looks kind of like a T with a very, very big top and a very, very small, vertical section. Now this is referred to as a dip and strike symbol, and this is how geologists take this information and put it onto a map. So if we just jump to the next page, okay, so here is our dip and strike symbol. Now this is what it would look like on a page. So here we have, there's the long bit, which we just saw here. There's the short bit, which we can see here, and here's the 30 degrees, which we can see here. So on a map, it would look like this. So what does this all mean? Well, the yellow bit, that's the dip direction. Okay, so that's telling me which direction my layer of rock is dipping. The angle is written as a number, so that's the dip itself. So dip direction in yellow, dip angle in pink, and strike, remember, is 90 degrees, the dip direction, in blue. Okay, so once again, dip, dip direction, strike. So how do we put this onto a map? Well, it just so happens here we have a very nice example of what's going on. So if we just ignore this top bit, as a geologist, I would walk through this area, okay, and I would go, right, as I'm walking along, I'd collect, I'd look, right, in this area I have mudstones, this ridge here is made of sandstones, here I have limestones, back to a sandstone again, I have mudstone here, sandstone, limestone. So as a geologist, I would walk around the area and I would go to every single location I could, and I would first of all work out what the rock was. Okay? And when I was at those locations, if I could, I would take dip and strike measurements. And so at each of these locations, I would try to collect information from any pieces of rock that looked like it had a bedding plane like this, which I could take a measurement of. And so as you can see in this particular instance, they've managed to collect 3 measurements from the sandstones here. And so what are these measurements? Well, you can see this sandstone here has a dip of 30 degrees. It's dipping to the west, so off to the left, and the strike is approximately north-south. And so what this means is, even imagine I didn't have this view of the subsurface, okay? Imagine I couldn't see this. Imagine all I had was this map here. It means that in my mind, I can already work out that this piece of rock is dipping down 30 degrees like that, even if I didn't have this information here. Okay, what about these 2 layers? Well, I also know that this layer of sandstone here is dipping 85 degrees, so very steeply, near vertical, and it's dipping this way, off to the east. So I know that I have a layer of sandstone that comes up like this, and then dips down very steeply. So it comes up and down. So I have myself an asymmetrical fold, don't I? I have myself an asymmetrical anticline. Because I know this layer of rock is dipping down like this, so dipping down towards the west. This layer of rock here is dipping down towards the east, so I'm coming up, and I'm coming vertically, almost vertically down. So up and vertically down. So I have an asymmetrical anticline. As I come over here, I have another dip and strike symbol. That's 40 degrees, it's pointing towards the west. So I have this layer of rock here, which is coming in near vertically to the east. And I have this layer of rock here, which is coming in at 40 degrees to the west. And so they're going to meet up, and here I'm going to have a syncline. So you can see these symbols, tremendously helpful things. Now, why do we have the strike? Because what the information we've just gotten there is we can get exclusively from the dip direction, can't we? The strike is essentially telling us the orientation of the feature, isn't it? So if you look at the strike, in all these cases, it's telling us that these sandstone beds are orientated approximately north-south. Okay, and that's very, very important, because we want to know where our layers of rock are going, don't we? So the dip direction and dip tell us which way the layers of rock are going, but we want to know the orientation of the feature as a whole. And so that's where the strike is important to us. So if we look at these features here, so if we look at these 2 diagrams, we're actually going to stop here in just a second. So if we look, we can see here we have an anticline and syncline. Okay, so let's just think once again. Anticline, oldest rocks in the middle, youngest rocks on the outside. Syncline, youngest rocks in the middle, oldest rocks on the outside. Okay, so if I was to look at these 2 rocks, now imagine this is what I actually saw. So we're looking at this area on top. Okay, so as a geologist, I can't see what's going on here. I can't see what's going on here. All I can see is this stuff on the top. So if I look at it, I would see a purple layer, a yellow layer, red layer, yellow, purple. Now once again, these repeating layers are a classic indication I have a fold. That's the first thing as a geologist I would see. I would go, right, purple here, yellow here, yellow here. Right, repeating layers, that suggests a fold. The next thing I would look for is I would look and see if I could get any dip and strike measurements. And so what I would see in this case is I would see I had, for instance, the yellow bed would be dipping off towards the left here, whilst this yellow bed would be dipping off towards the right. So this yellow bed would go this way, this yellow bed would go this way. And because one was dipping this way and one was dipping that way, it would form an anticline, like so. In the case of the syncline, once again I have the repeating beds, don't I? Instant indication I have a fold. And so what I would see is if I was looking at the yellow layer again, I would see the yellow layer dipped. This yellow layer was dipping to the right, and this yellow layer over here was dipping to the left. So they were both pointing towards each other. So obviously I have myself a syncline, don't I? And so that's exactly how it works. As a geologist, you'd see these repeating patterns. You would say, right, that looks like a fold. Then you would look at the dip and strike symbols. If you can get that information, you would say, right, if they're dipping away from each other, it's an anticline. If they're dipping towards each other, it's a syncline. That simple. Okay, I will keep going, but you know what? This is the time to stop part 3. So once again, stop the video, water, tea, coffee, whatever you want. Relax for a bit, then come back for part 4. All right.